In this paper we present StereoSyn, a framework for stereoscopic image editing. The proposed framework offers patch-based solutions to a wide variety of stereoscopic image editing problems. Patch-based techniques have been proven successful for image editing. However, individually applying these algorithms to synthesize the left and right views would unlikely establish a consistent 3D interpretation of the resultant stereoscopic image. Our method adopts an optimization-based approach which minimizes the appearance distance between the source and target images. In order to maintain a consistent 3D interpretation, we segment both pairs of images into three regions: the pixels only visible in the left view, the pixels only visible in the right view, and the pixels visible in both views. The image appearance distance is defined as the combination of bidirectional distances of the three regions. The first two distances measure the differences between nearest neighbor patches and the source and target images. The last distance measures the differences between nearest neighbor patch pairs and the source and target images. For the patch similarity metric, conventional texture synthesis algorithms define the similarity of two patches as the sum of squared distances of corresponding pixels colors within a window. For stereoscopic image synthesis, we need to take 3D geometry differences between patches into account. Therefore, we introduce the depth-dependent patch pair similarity metric, which consists of two terms. The depth structure resemblance term measures the distance between their local depth structures. The depth-dependent color similarity term measures the color distance between pixels but emphasizes more on the pixels with similar relative depths. The depth-dependent weighting kernel penalizes the color discrepancy more at the pixels with more similar depth structures. Here we give an illustration of the weighting kernel. In this example, we compress the disparity range of the source image to synthesize the target image. We focus on the two patches centered on the pillar. The weighting kernel penalizes the color distances more on the pillar and less on the wall, since the central pixel is part of the pillar. For more details, please refer to our paper. We give a comparison of our proposed similarity metric and two other simpler methods. Simple 4D, which directly sums the distances of both colors and depths together, and our metric without the depth-dependent weighting kernel. The detailed views show that the two simpler metrics often produce blurry results. Without the depth-dependent weighting kernel, the pixels from different layers could be mixed up. We applied a multi-resolution iterative algorithm to optimize the objective function. In the synthesis step, the joint patch pair search is proposed for handling the corresponding information in both views. We show several results generated by our method. Each result is shown in red cyan anaglyph image with a 3D visualization. We give a comparison of our method to the warping-based method for the content adaptation application. The warping-based approach leads to visible distortion if there are significant disparity variations within quads. It is because the pixels with different disparity values in the same quad usually need to undergo different transformations, which is impossible for warping-based methods. Our method allows each patch to contribute only to the regions with similar local depth structures, and thus can generate visually pleasing results.